Now let us discuss about reluctance. In electricity, we have EMF is equal to IR, where I is the current and R is the resistance. Similarly, in magnetic field, MMF is defined, that can be represented by F is equal to the flux times the Rm, that is reluctance of the material. Reluctance. So from here, if we define the reluctance here represents the opposition of the magnetic flux in magnetic circuit, similar to the resistance that represents the opposition of the current in electrical circuit. And from this equation we can write magnetic flux is equal to MMF divided by the reluctance of the material. And to keep MMF constant, if Rm is increasing, then flux should decrease. It means that for same value of MMF, that is current applied, flux will be less in a material with high value of the reluctance. It means that the material will offer more opposition to the magnetic flux through it. And from here we can write reluctance is equal to the MMF divided by magnetic flux. And MMF, we already know this, that is Ni divided by flux is equal to Ba. B is mu Ni times area of the core. And after further simplification, we have Ni mu naught. This can be written as total number of turns divided by the length of the N by L, I, A, both I we can consider same, A, and from here we can cancel out these two terms and the net value will be L divided by mu naught A. This is Rm. Can we relate this from some equations that is well known to us? That is, resistance is rho L by A. It is the resistivity of the material that represents the opposition, whereas mu is the permeability of the material. It represents how much allowances will be given to the flux in the magnetic material. We know that the reciprocal of R, that is known as conductance. So reciprocal of R, that is 1 by R, is conductance. Similarly, in magnetic field, the reciprocal of Rm, that is 1 by Rm, is permeance. Permeans. And in this way, if we try to find the analogy between the electrical and magnetic circuits, then we can have between electrical and magnetic circuit, then In electrical circuit we have the EMF, whereas in magnetic circuit we have MMF. And here we have current. The analogous to this in magnetic circuit is the flux. Here we have the resistance rho L by A. Similarly, in magnetic circuit we have Rm, that is 1 by rho L by A. This is reluctance, resistance, reluctance. The inverse of resistance is conductance. Similarly, the inverse of this is P. The inverse of reluctance is permeance. And in electric field, the current density is J is equal to sigma E, where E is electric field and J is the current density. Similarly, in magnetic field, B is equal to mu H, where H is magnetic field intensity and B is the magnetic flux density. Now let us solve some example to find the inductance in case of solenoid. So the first problem is the inductance of a long solenoid of length 1000 mm wound uniformly with 3000 turns on a cylindrical paper tube of 60 mm diameter. We have to find the inductance for the case the solenoid is wounded on the cylindrical paper tube and the radius of the cylindrical paper tube is it is diameter, so R will be 30 mm, that is 0.03 meter, and the length of it is that is 1000 mm at which it is wounded. So this length is 1 meter as it is given in meters, so put all the lengths in meters, and N is 3000, and the formula to find L is mu naught N square A divided by L. A is, suppose it is wounded 1000 turns at this, then the cross sectional area of the core at which it is wounded, that is this one. So area is the cross section. So we know A from the radius, we know L, we know N, mu naught. We can assume if it is not given, then that is the 4 pi into 10 to the power minus 7, that is the standard value. So from here we will put the values, that is 4 pi into 10 to the power minus 7, N is 1000, area is circular, so it will be cross sectional area will be pi r square, so pi r is 0.3 square, that is 1. So when we will solve this, we will get 31.97 millihenry. So this is the inductance for this case. The problem is very simple. Now come to next problem, that is a long solenoid with 15 turns per centimeter. So we can say N by L. N we know, length we know, so has a small loop of area 2 centimeter square placed inside normal to the axis of the solenoid. So if the current carried by solenoid changes from 2 ampere to 4 ampere in 1.1 second, what the induced voltage in the loop while current is changing. So we have to find the induced voltage, and to find the induced voltage the next important parameter that is required to know is the changing flux. If changing flux is known, then we know EMF, and to know the flux, it is important to find the magnetic field density. Yes, so from there we will start to find magnetic flux density B, and formula for that is mu naught Ni. Before coming to the direct solving the problem, let us have look on the image that is formed from here. It is said that this is the solenoid with 15 turns per centimeter, and due to this solenoid the flux is changing, and the axis of the solenoid is this. 2 centimeter square area, a loop is placed that is normal to the axis as it is given here. The cross sectional area of the loop is 2 centimeter square. Now we have to find the EMF induced in that. To find B, we know mu naught, we know N, that is 15 turns per centimeter. So 15 turns divided by 0.1 meter I. So from here we can write mu naught 1500 I will be magnetic flux density, and if we wish to find the flux, then that will be BA, and area means the flux through this we are required to know, so that we can find the EMF in this. So flux through this means area of this loop. So flux, the magnetic flux will be magnetic flux density times area, that is mu naught 1500 I times area will be 2 into 10 to power minus 4. This is the flux. And now if we want to find the EMF, then that is nothing but rate of change of flux. So the rate of change of this, that is mu naught is constant, 1500 is constant, into 2 into 10 to power minus 4, that will be area as it is given 2 centimeter square. And the remaining term is I, so the di over dt is left. So E can be written as mu naught 1500 to 10 to power minus 4 di over dt. From here we can write 3.3 mu naught into di over dt. And as it is given that considering the change is uniform, then di over dt is 0.3 mu naught final minus initial, that is 4 minus 2 ampere current, in time, change in time 0.1 second. So from here we can have 0.6 divided by 0.1 mu naught, that is 6 into 4 pi into 10 to power minus 7 old. This is old. When we will simplify, it will give us the final value. So this is the EMF that is induced in the coil that is placed at the normal to the axis of area 2 centimeter square inside the solenoid. So this is the final answer. Now let us discuss Maxwell's equation that combines all electrostatic and magnetostatic laws in a set of equations, and there are static and dynamic fields. In case of a static field, the electric and magnetic fields are independent from each other. However, in case of dynamic field, electric and magnetic fields depends at each other. So let us discuss the static field case first. When the field is static, in that case the equations can be defined in differential form and in integral form. The Maxwell's first equation relates to the Gauss law we have studied in electrostatics, that is del dot D is equal to the rho V. This is known as the first this is known as Gauss law, that is first equation of Maxwell's. And the second equation is related to the magnetic field, that is del dot B is equal to 0. We have derived and came to know that magnetic monopole does not exist. So for reference we can write here Gauss law, and this is no monopole in magnetostatics, in magnetism. And this is the second law of Maxwell's. And third law was related to the electric field, that is the curl of electric field is 0 for static field. It shows that the static field E is conservative in nature. So for this third equation of the Maxwell's, we can write for static field, that is electric field here, for static electric field has conservative nature. Okay, and for fourth equation of the Maxwell related to the magnetic field, that is the curl of magnetic field is the current density. If we revise, then we find that this is Ampere's law. So these are the equations of Maxwell's in differential form. In integral form, this is just the d dot ds for the closed surface. It is flux, that is charge enclosed. D dot ds is equal to the charge enclosed. This is the integral form of first Maxwell's equation. And the second, for this we have B dot ds for the closed surface is 0 in case of the integral form of the second law of Maxwell's. And the third law, that is showing the non-conservative nature, showing the conservative nature of electric field, related to that in integral form it is E dot dl is equal to 0 for a closed loop. And similarly, fourth law we can write H dot dl is equal to the current enclosed. That is related to the Ampere's law. It is Ampere integral form of Ampere's law. So the first Maxwell's equation is related to Gauss law. Second is related to the magnetism, that is the monopole does not exist. Third law related to the electrostatics, that is the field has conservative nature. And the fourth law is related to the Ampere's law in magnetism. And if the field is not static, means we have the dynamic field, in that case dynamic field case, the we know that charge, when charge is moving, in that case there will be, when the moving charge is called current, and due to that the field will be there. And in this way we can have, there is a magnetic field when the charge, that is current, is flowing. In this way both have relationship, one depends on another, means electric field depends on the magnetic field and magnetic field depends on the electric field in the dynamic field conditions. So for that case the Maxwell's equation changes in differential form and in integral form. Let us revise them. So the first equation remains as it is, there is no change. And second equation also, monopole does not exist, it also does not change. Now the third equation, that is showing the conservative nature of the field, when it is varying there will be a magnetic field, and that is del curl of E will be rate of change of magnetic flux density. If B is time varying, then we will get this relationship. That is the third law of Maxwell's in the dynamic field. And the fourth, it will change by adding, it will cause the electric field, and that will be curl of H will be J plus the change, due to change electric dt will be there. Okay, a time varying E also produces B. Okay, epsilon naught E mu naught B by mu naught. So time varying E also produces B or H. So in case of dynamic field, the equation modified by adding the additional term that exists due to the variation in the E. And in integral form, equations, the first and second equations remain same as it is. So that is related to the Gauss law. ds is equal to charge enclosed for the closed surface, and the second equation also remains same, that is for the closed surface B dot ds is equal to 0. But third equation changes and it becomes E dot dl is equal to the del B over del T dot ds. It varies like this. However, and in fourth equation it changes, H dot dl in a loop is equal to the J plus this dot ds. J plus dot ds. Okay, so in dynamic field, Maxwell's equations first, second, third and fourth in differential and integral form. In a static field, differential and integral forms of Maxwell's equation are presented here.